So this is the length is 1500, capital D is 500, thickness 3. This is the diameter of steel, right? Steel tube.
No, sir.
Then
That's the diameter of the concrete. It will take 6 mm, sir.
okay. So let us first make the concrete. Now we'll work in mm. Okay.
Okay, sir.
In mm it becomes easier. So see, while making this circle, you just cannot click like this to end the
Okay, sir.
circle. Always make sure that you start from the center and you are clicking on either of the axis, because that whenever you the point where you'll click it, that will be your junction joint for this circle. So always keep it on either x axis or y axis. See, the joint is on x axis now, because it becomes easier for meshing. Later while meshing it becomes easier. So diameter is 500, that means radius is 250. So this is my concrete. I will save this sketch so that while making steel it will be easier for me. Done. What is the length? 1500.
1500.
1500 means 1500.
Yes, sir.
That means 1.5 meter. Now let us make steel, and we will go with solid element only for steel also.
Yes, sir.
So now I will bring the sketch that I have saved, and the thickness of the steel is 6 mm, right?
Yes, sir. 6.
So if it is 6 mm, then what will be the radius? 250 plus 6, 256. 256. Okay. So the distance between these two, it's 6 mm. Okay.
Yes, sir.
Simply save it and make it 1500. Now one thing I have observed, that see, in real in this experiment, while performing experiment, what happens, let's say this is your concrete and you have the steel. Now we try to make this or is this, let's say this is my steel and I have compacted my concrete, but doesn't matter how accurately you make this sample, when applying at the time of application of load, you will find out that initially there is no concrete, because when you pour the concrete, you have wiped out the top portion. There will be minor gaps like 1 mm or 0.5 mm gap, due to which you will find that concrete is available, strong concrete, or the concrete which will actually take the load, that is available around 1 mm below the steel. Let's say if this is my steel, then somewhere just 1 or 2 mm below you will find that concrete is available. So what happens when you are applying the load using the UTM, then first load that is getting transferred is on the steel. Concrete takes little bit later, because the top portion of the concrete is not that much accurately placed, or due to which if you do not consider that, I have found that from my experience that the modeling result is not accurate, failure and all. So what I will do for concrete, I will shorten it by 1 mm, just 1 mm, like instead of 1500 I will make 1499. So what will happen? I'll bring this both of this here, and it's a very minor difference, but it gives you problem while analysis. So let us mark the center point for the steel. So this is my center point for the steel. And let us mark the center point for the concrete. So see, both are 1 mm, both are at 1 mm difference. So what I will do, I will simply translate this one from this. I translate the concrete from this point to here. Now if I switch on both of this, see, if I show the transparent view, see, there is a small gap at the top as well as at the bottom. And what is the gap? This gap is 0.5 mm and the top is 0.5 mm. So this is okay. And I found from my experience that if you do not consider this, what happens? Concrete directly starts taking the load, and it gives you a failure like elephant foot failure. This is called elephant foot failure. What do you mean by elephant foot? If you have seen an elephant foot, you will see that at the bottom of his foot, due to excessive load, it bulges like this, isn't it? The elephant foot. So that is called elephant foot failure, and this is the technical term, so you can refer it. So we just want to avoid that elephant foot failure. Okay. Now you don't have to mention this to anywhere, because people won't understand it why you have kept 1 mm shorter, but it's okay. I'll rotate this and I'll make it vertical. So I'll rotate it about x-axis. So first point was 0 0 0, and next point any point in x-axis, and y and z will be 0. And I want to rotate it. Sorry. First point will be 0 0 0 0, and any point in x-axis, y 0, z 0. Now I want to rotate minus 90 degree. Minus 90 degree will give you a rotation of clockwise rotation. So it has become like this. Now see, if you see the question that you have asked, how much load shall we be applying, isn't it?
Yes.
See, they have given U1 U2 0, means what is U1 over here? U1 is x, right?
Yes.
U2 is y and uz is 3. U1 x, U2 y and U3 is z. So vertical
Yes.
direction is U3. So U1 U2 0 means lateral movement is restricted, right?
Yes.
and U3 is 0.04 L. Means in the vertical direction they have applied displacement control load. Are you getting me? Vertical direction
Yes.
displacement control load, and what is the displacement that they have applied? 0.04 L. L is 1500.
Yes.
That means if you multiply 0.04 with 1500, how much? It's 60 mm. That means they have applied 60 mm vertical displacement.
Displacement.
Okay. So 60 mm vertical displacement, and see what is the strain in 60 mm vertical displacement. What will be the strain? Change in length upon original length, right? What is original length? 1500. Change in length 60. 0.04. Can you see it over here?
Yes, sir.
So they have applied this. Now let me check what type of step they have used. We can go for dynamic explicit, but
They have used static risks steps.
static risk. Okay.
Risks.
We'll go for interaction first. Let me check what they have used.
Surface to surface interaction with the 0.5 friction they have used.
The steel tube and film of the surface of contact steel tube. The normal way was the hardness. Okay. Steel tube. As a problem the tangential diagram used in this study. Sliding is almost no. Friction coefficient is, they have used 0.5 friction coefficient.
Yes, 0.5.
The rigid body element was used to make elastic model also we can have the tie constant was adapted to the between the constant the loading plate steel tube and the loading plate. The loading plate was selected as master surface on the top surface. Okay. Create a loading plate. The diameter of this loading plate will be 270. Thickness will be, let's say, 10 mm.
Sir, can't we do without a loading plate? Will it give any changes when it will?
No, we can do it, but they have used loading plate. What changes you want? Like, see, you are not using their property, you are not using anything of that. So what is the problem?
No, no. Without the loading plate, if we are directly
Is it
analyzing.
can be possible, but see, they have used rigid plate, so I just want to go for that.
Okay, okay, sir.
No problem. You can simply use rigid body constraint or coupling, and you can simply apply it. They have used, that's why I'm just.
Okay, sir.
So here first is steel and concrete. Let us check which one is master. Master surface is most probably the steel only. Yes, and then the slab surface is concrete. Okay, and then loading plate and concrete and loading plate and steel are tight. So the bottom portion is tight. The top portion and bottom portion are tied with the loading plate. So these two, this one and this one will be tie constraint. You can create it separately. I'm just using a tool to directly create it. And then
Actually, I'm new to ABAQUS, sir. I've not used it.
I'll show you. And this is getting recorded, so you can directly do it, no problem.
Yeah, okay, sir.
And this one again tie, and this one again tie. So this one is tie, and here interaction, so I just have to create a property, contact property, tangential behavior penalty 0.5 friction. Okay, and the normal behavior tangential behavior, just keep it like this, so it takes automatically. Okay, you can create one by one also, like surface to surface contact. Then it will ask you to select master surface. You select the inner surface of the steel as master surface. Here you can switch off. Let's say I want to select the inner surface of steel, so I'll have to switch off everything apart from steel. Then I'll just have to select the inner surface is selected, done. Then I'll have to select the slab surface. So now I need to select the outer surface of concrete. So likewise I can create one by one, or there is an option, this one, if you just find contact pairs, so it will automatically find you the contact pairs available in the model. So you just have to switch on everything and just you have to check which one is connected to the model. So I have switched it on. If I click on this, see, if I click on this, it shows that the steel and concrete are connected. How? If you switch off this, you will understand better. Okay, see, only steel or concrete and connected for this interaction. And if I click the second one, that means it is connected to the bottom portion. So like the top portion of the plate and bottom portion of the concrete and steel are tied. Tie means you have fastened it. Okay. So as I have already created, so I will not create again. Interaction is done. Now I'll have to create the boundary conditions. So for that, I'll again go to interaction, and I'll use rigid body constraint. First I'll create a reference point for the loading plate at the top. I'll switch off the steel and concrete. I'll keep the loading plate only. So both the top and bottom reference points are created. Now create rigid body constraint. That means all elements of the plates will behave like a rigid body. Top RGB rigid body. So it is asking me to select the elements. So it will be the top elements and the nodes that I want to tie. This node and the reference point, that means this one. So see, all the nodes of this plate are tied to this reference point. That means if this reference point will go up, that means all other points on this plate will try to go up. It will follow the same behavior as that of reference point. Similarly, I'll have to do it for the bottom, right? Are you getting it?
Yes, sir.
So for the bottom also, again select the bottom plate, then select the nodes for the bottom plate and select the reference point. Okay, done. Now I'll apply boundary condition. So for that, I'll go to step first.
The reference point will be created on the plates, no, sir?
Yes, it has been created on the plate only. Now step here, we have the option, we can go for static general, static risk, etc. So let us go for static general first. If it gives convergence issue, then we will go for static explicit. Static general, and displacement that we are applying is let's say we'll apply it in 10 seconds. Switch on this, use some damping, and then make initial increment maximum 0.2. Okay. Here are the outputs that you need, so I don't need these many outputs. I'll first request U and RF, that will be sufficient for me. and I don't need for all points. If I get 30 intervals, that will be okay. If I get
Sir,
30.
ma'am has asked me to plot. Sir,
Yes, yes. So you are recording, right?
yes, sir.
Because I have paused it mistakenly. Yes, by mistake I have paused it. Where is that? Order. Yeah. It was here. So at the bottom, see U1, U2, U3, UR1, UR2, UR3, all are fixed. So I'll simply use fixed condition. And the top, so I'll use this one, displacement rotation. Top, U1, U2, U3, everything will be fixed. And in the step where we'll be performing the analysis, there I'll switch off. Here I need 0.04 L means 60 mm, okay, and it will be minus 60. I'll apply an amplitude, so this amplitude will be equally spaced, tabular, it will be tabular. At 0 second the amplitude will be 0, at 10 second the amplitude will be 1. So this one will be multiplied with 60, and finally at 10 second total load will be applied. So you can go with tabular, or rather let us go with smooth amplitude. Okay, let it be there. I'll plot another smooth amplitude. I'll show you the difference between these two, why I am using this. See, I have entered same data, but for smooth amplitude, what will happen if I plug in tools, amplitude plotters? See, if I plot the smooth one, this is how the load will be applied smoothly, okay, in this pattern. And if I simply click tabular, then it will be steep, so that I don't want, so I'll keep it smooth. I'll save the model. Load application is completed. Now remaining is meshing, then material. I always assign the material property at the end, so that's why. So for meshing, what I'll do, I'll use uniform meshing for everything. So I'll make, see, if I try to mesh it in assembly now, it shows that dependent part cannot be meshed. Why? Because these instances are dependent. Now I'll have to make independent. So what I'll do, if you want to make independent, if you want to mesh dependent part, then you'll have to mesh it in part one by one, okay. And if you want to mesh it in assembly, you just have to make everything independent. So yes, this model is okay because only 4 or 5 instances are there. These are called instances, okay. But if there is, let's say, some for complicated model 100 instances are, in that case we always prefer to mesh it in part, or if you need different meshing for a part, so there we always go for this type.
Part wise.
Here I'll change the meshing technique to medial axis, because I have seen the circular part. This circular part, using medial meshing technique, we obtain better mesh. Even if you don't change, no problem. Let us, what is the mesh size they have used?
B by 10, that is D by 10,
50 mm, okay. 50 mm is okay. They have used 50 mm. Simply select everything and mesh it. Okay, so see, mesh quality is quite better. Before that I just have to check one thing. I'll hide this too, and I just want to check whether these points are matching or not. Okay, see, there is a problem. These nodes are not matching, so due to which there is an overlap. Okay, see, can you see this? This concrete is merging with the overlapping with the steel. So what I have to do to make sure that the meshing is such a way that this portion is not creating any such issues. So in that case I will just try to change the meshing technique for these two again, and I'll see if this works. No, did not work. So for that, first thing that I'll do is I'll partition this, and I'm just creating partitions so that I want to make sure my mesh is exactly matching with each other. So create partition for these two models. So I'll use this tool. Partition is done just for this type of requirements where we don't get uniform meshing. We just divide this solid in different parts. That doesn't mean we are creating cuts. No, this does not represent the cuts. It only represents that we are simplifying the geometry. Yellow color means meshing is better but not the best. When you get blue color, that means, or green color, I don't know what do you call. I have color blindness. So yeah, let us just check now. No, it did not match. Let me try to change the meshing technique. It's not matching. I have to do something to match it. Check the top view. Okay, this one worked. Yeah, now see, this is exactly matching with each other. That means my problem is solved. Now this is a good meshing. Everything is done. I'll just have to assign the property. So first I'll create the property for loading plate. LP density is, let's say, 7850, not required, but still I'll give. Modulus of elasticity they have given over here.
So what are the unit consistency that we have to maintain for the properties?
Properties, as I have said, I am working in mm. So wherever you are working, entering the properties, always you have to enter those in properties in mm. If you see this ABAQUS unit, see, simply type in Google ABAQUS unit. Okay, alright, my PC is not charging. Yeah. ABAQUS unit, and you'll get this image. So here see SI, if you are working in mm, these are the units you will be entering for time, second, mass, kg, stress, pascal, that is Newton. If you are working in mm, then density will be density, see at the bottom it is density, it will be ton per mm cube in SI mm, but if you are working in SI meter, it will be kg per meter cube. So the density that we have entered is wrong, it is in kg per meter cube, it will be e to the power minus 12, it is in ton per mm cube. Okay. Now hold on. So they have mentioned 110 to the power 12 MPa, 1 e to the power, and Poisson's ratio as 110 e to the power minus 7. So this will be for the loading plate. We have to create the section, make it empty. Click OK. Okay, done. Next is for steel. Now for steel, I'll have to get the stress strain property. In that case, what I'll do, there is an tool that you can use. Now here just enter the modulus of elasticity of steel. It's yield stress of concrete is steel is 690. Okay, so the yield stress they have given 690, and modulus of elasticity, thus they have given the modulus of elasticity of steel
Yes, sir. Your 200 gigapascals.
200 gigapascal. So simply enter 200, and in MPa it will be 2 lakhs, isn't it? 2 lakhs. And yield stress they have given 690, ultimate stress 753. See here they have given ultimate stress, no, 770. Ultimate stress is 770, and the maximum strain at rupture. So FTO strain at rupture. So ultimate strain it is 0.065. Okay, so it will be in percentage 0.065, 6.5%. Okay, so this is the stress strain curve that we have got, and you can directly use it. Okay, we'll use engineering curve. Okay, no problem. If see in my PC it is not working because my Excel is not activated, but you can if you just simply click on this, you'll get the stress strain curve data. But we have this, we can directly calculate it from here. Why it is not activated?